Hello everyone. I hope you and your families are all keeping well. Happy Easter, and I hope you enjoy this time. So we are moving to chapter 3 and we are going to talk about system response. Previously I mentioned that most of the time the response that we see in a system is the steady state response, and that means that temporarily we might see some variation in the response of a system, but over the time they die down. This is the word that book is using, the phrase that book is using. They die away or die down, and a steady state response remains. And that is the one that we rely on. So, first example that chapter 3 is looking at is this spring. And I'm going to read from the first paragraph. Forgive me if I pronounce some English words not correctly. So, the total response of a control system or element of a system is made of two aspects: the steady state response and the transient response. The transient response is that part of the system response that which occurs when there is a change in input and which dies away after a short interval of time. The steady state response is the response that remains after all transient responses have died down. And this example, this spring example, is showing that. What happens when a weight is suddenly suspended from spring? So here I'm imagining that I have a spring and there is no weight, and then I have the spring and the weight is suddenly added. Or you can think vice versa. You have the weight and you remove the weight all of a sudden. So I have this animation that is showing what will happen. Before I play that, you see that the spring is jammed. The point is very high, and then when the weight is added, it is stretched and it comes lower. So we have these displacements. But before that, we will have some bouncing. I want to look at exactly what happens. The bouncing will be high at the beginning. I don't know if you have noticed that in any system that has a spring or similar scenario. And then it slows down. That's the plot here. Will explain that. I'm going to play the animation. Did you notice what happened? It started at very high bouncing and slowly down until it goes to non-moving state. That part is the steady state part, and this part is the transient part. It's temporary. It dies away or down, that is the phrase, dies down. And this part remains. That is the part that we rely on. So the steady state part is the one that remains, and transient part is the temporary part. Keep that in your mind. Now, if you want to put that imaginary black box around this system, we are going to look at a system like this. What is the input of this system? What is the input? The input is the weight, right? And the output of system, what is it? What do we expect to happen? Yeah. The displacement is the output of the system. So that box is in place. The weight or mass is the input. And the output is the displacement. If you notice, I have t here. That is not a multiplication. That is the form that we use to write, for example, if you want to write f of x. So when we say f of x, the f is in respect to x. If we write f of t, we are not saying that t is multiplied in f. We are saying that f is in relationship with t. So here, d of t means that in different time, the displacement is different. In other words, the displacement varies over the time. The weight varies over the time. So what that means exactly? In transient response, when we have that bouncing going on, you notice the displacement varying over the time. But when we are looking at the steady state, they are fixed. So the time is settled. Over a period of time, after that transient time is gone, we will have constant values. But before that, we will have depending values. Now, from now on, we are looking at differential equations to describe a system. It's very important. And the book is saying that differential equations are describing behavioral control system or one element of a control system. It doesn't have to be the whole system. It can be only one element. To remember the elements that we discussed in previous chapters. Now, here we are saying that the transfer function, or here we are looking at differential equation, might only describe a part of that, not all of it. But it is very important to know that all of them are in respect to time. That means that if we are looking at the derivatives, we are looking at the derivative in respect to time. And we are looking at two kind of systems. We are looking at first order, this is for first order, and second order systems. I have one example to show you. By the way, this example was on page 78 of the book. Now, the next example, we are going to look at this system that is showing a water tank. Water tank is very familiar for you guys because you have done lots of programming in PLC lab, how to control it, what kind of control system you can use, and so on. So it is very familiar for you. I'm going to look at this float. The float shows the level of the water in this tank. And then this yellow part, imagine, is the part that water can come in. But please notice, it is designed in a way that by the time that this float reaches the desired level, here is capital H, that will be closed. So no water can come in anymore. A simple design to show how a float-based water valve control system can work. Now, if we want to look at the differential equations, what we can say about this system? So the movement, the level of the water, which directly depends on the time, we are going to call it small h. And the desired, the maximum level of the water, we are going to call it capital H. So at the beginning, the small h will be low, and slowly it will go higher, higher, higher until it reaches to h. So we are looking at the difference between the a capital H and a small h. So the rate of change of height is proportional to the subtraction of these two. Capital H minus a small h. The difference between these two. So how we write that mathematically? We will have a constant between them, and then the rate of change of something is derivative of that over the time. So derivative of small h over t will be proportional to h minus h, and then there will be this constant between them. Now, we know that when it is filling up, at the beginning, it is very fast. But then, because of the system, because of this thing covering the whole, it becomes slower and slower until at some point it stops. If we want to plot that, it will look like something like this plot. As you see, the derivative is very high. At this point, if we want to calculate the derivative, it will be near 1. You see that? And at this point, if we want to calculate the derivative, it will be near 0 because it is becoming flat. Do you see that? This line here is showing the maximum h, the maximum level. And then you see that here the derivative or rate of change is very high. And it becomes low and low and lower until it becomes very close to 0. Now, if you want to do a mathematical equation representing how this plot is behaving, sorry for that, I'm going to put that in place. Now, we are looking at this equation. I want to have a small h in one side and t in the other side. This plot is familiar. It's exponential plot. How it is behaving? So we know that we will have a negative in power of that exponential. Another way of getting that is from that equation. But for now, we are just looking at a typical exponential plot. And I have small h in one side and capital H in the other side. And then I have this multiplication in 1 minus exponential of power minus kt. And this is how we understand this system works. So, imaginary black box or blue box in this case on top of the system. What is my input? My input is the level that I want, capital H. And what would be the output of this system? Small h. I hope it is clear and you all understand this part. I'm going to have more examples in next video. If you have any question, send me email. Thank you. Take care. Bye-bye.